Developers are currently caught in a vice. Lumber prices are highly volatile, swinging up and down from quarter to quarter, while the skilled framing labor required to assemble those materials is steadily aging out of the workforce, leaving job sites stalling out. The market's response to this bottleneck is cold-formed steel, or CFS. Developers often treat cold-formed steel as a simple material swap for wood, an assumption that fails to account for the procedural shift required to make it work. A traditional wood framing mindset relies heavily on field improvisation. If a rough opening is off or a pipe needs to move, the crew simply pulls out a saw and makes the adjustment right there on the site. Attempting to build with panelized steel using those legacy wood workflows will rapidly hemorrhage money. Success with steel requires moving away from the standard construction philosophy and treating the job site like a manufacturing assembly line. This chart illustrates the shift in planning. Traditional wood framing has a short pre-construction phase followed by a long on-site build. With cold-formed steel, a heavy, time-intensive pre-construction phase compresses the on-site assembly. But once fabrication begins, design changes become structurally impossible. Capturing the advertised savings of steel framing requires paying a strict organizational price up front. That organizational price starts with exhaustive 3D structural engineering. Machine-integrated software modeling must be totally finalized before ground is broken. That digital data feeds directly into panelized roll-forming machines, where raw steel coils are rapidly shaped and punched into hyper-precise structural components. The output is a kit of parts. Panels arrive on the job site pre-labeled and ready to assemble, removing the reliance on highly specialized carpenters. Because the panels fit exactly as modeled, on-site assembly can accelerate by 30 to 50%. This speed depends entirely on strict MEP coordination, managing the mechanical, electrical, and plumbing routes. Every pipe chase and electrical run must be permanently locked during the digital pre-construction phase, so the roll formers can punch the service holes in advance. If a client walks the site and decides to move a toilet or an outlet by 3 feet, the workers cannot simply cut through the load-bearing steel panels to accommodate them. Panelized steel removes the possibility of field adaptability in exchange for predictable, rapid execution. Committing to steel restructures your capital risk. You have to purchase materials early and pay specialized third-party structural engineering consultants well before you see vertical progress. While steel provides stable material pricing compared to the swings of lumber, it can cost more per linear foot depending on current market conditions. The financial justification for developers is often found in the long-term impact on builders' risk insurance. Insurers offer heavy discounts for steel structures because the material is non-combustible and completely immune to termites, mold, and rot. This bar chart visualizes that impact using the example of a 4-story hotel in Ohio. The builder's risk insurance for the wood-framed version is $1.6 million. For the exact same building framed in cold-formed steel, the premium falls to $360,000. This $1.3 million return on investment is a delayed dividend, realized only once the policies are underwritten and maintenance begins. The slight premium on upfront material costs is overwhelmingly neutralized by back-end risk mitigation and insurance savings. Steel also simplifies environmental compliance. Because it is 100% recyclable, builders easily secure lead points by virtually eliminating job site waste. Structurally, new steel builds must strictly adhere to current ASCE 7 seismic codes to ensure high performance. Existing buildings and retrofits introduce a different variable, the assessment penalty. Existing buildings are evaluated under a performance-based code known as ASCE 41. This photograph shows a physical 2-story testing structure used by the National Institute of Standards and Technology. Their research exposed a massive discrepancy in how the assessment code grades cold-formed steel. In physical shake table experiments, test buildings survived simulated earthquakes exceeding maximum considered levels with only minimal damage. This visual model shows the conflict. The physical building easily passes the actual shake test on the left, but the exact same structure fails a linear assessment on paper on the right, triggering a mandate to double the shear wall requirements. Applying legacy evaluation codes to cold-formed steel forces over-engineering, which can destroy the cost efficiency of the material. Cold-formed steel is a highly optimized, data-driven system, requiring total design commitment before fabrication. This suitability matrix helps determine if a project is a fit. The vertical axis tracks design fluidity, while the horizontal axis tracks the project scale. In the top left are high-end, bespoke custom homes. Custom projects often fail with steel because late-stage changes destroy budgets. But the safe zone for panelized steel is in the bottom right. The material thrives in multifamily housing, prefabricated modular units, secure data centers, and commercial structures. These projects are even more profitable in high-risk zones, where steel's fire and hurricane resistance triggers maximum insurance savings. The final rule for developers is direct. If blueprints and MEP can be locked early, cold-formed steel is a lower-risk investment. Do not buy steel expecting it to act like wood. Buy steel only when you're ready to treat the job site like a precision assembly line.